Hi, so a while ago, my students asked me to explain a case in biochemistry, and I did something that I've never done before. At the moment, I told the student that if I try to explain it now, I will make things more confusing, so I will try and explain things later because I realized this case included some mathematical equations. Calculations and also the chemistry calculations, and it felt beyond our study material and syllabus what we have to cover during the seminar. But I do not want to leave it without attention and leave it like without understanding. So I will try to explain this in a video, so for students who are interested in this case absolutely can go watch this video and understand the case. Okay, this was the case, the second case. A medical student is attempting to understand the buffering system of the human body and has set up the following experiment in the laboratory to help with their understanding. Consider a biochemical reaction that is taking place in a 0.1 mole of buffer. The initial pH is 7.4 and pKa of the buffer is 7.2. If, in a final reaction volume of 1 milliliter, 10 micromole of protons are generated, what would be the final pH of the solution? And then there are the options. So here I stated again one more time the values that are given in the case. There was the total buffer concentration of 0.1 mole. Initial pH was 7.4. pKa of the buffer was 7.2. Final volume was 1 milliliter, and the reaction generated 10 micromole of the hydrogen ions, H+. That means that we have generated more protons. So one thing we know for sure is that our initial pH is going to decrease, become more acidic. So every option where we have the pH above the 7.4 is instantly eliminated. So the next thing that we need to state is that in a solution like this, the buffer, two types of molecules. One is going to be the HA, which is going to be the weak acid, and the A minus, which is the HA but without the proton, is going to be its conjugate base. So for example, if you're thinking not this specific case, but if I were to give you an example of this, for example, we will have the carbonic acid, okay, and if we have like HCO3 minus without one proton, it's going to be the acid's conjugate base. So the next thing that we need to do is we need to write the only equation that we need to solve this case, and that is the Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation calculates the pH based on the pKa of the weak acid in a solution and the logarithmic value of the concentration of the conjugate base over the acid. Okay, so the ratio between the conjugate base and the acids. Now let's write it and clear it out. So pH equals pKa plus the logarithmic value of the conjugate base concentration over the weak acid concentration. Okay. Now we can put the values and that we already have from the case into this equation. So pH of our initial pH of our solution was 7.4, and it equals the pKa of 7.2 plus the logarithmic value conjugate base over the acid. So we can subtract the 7.2 from those equations. So 7.4 minus 7.2 equals the logarithmic value of the conjugate base over the acid. So the result of it will be that it will progress into something like this. 0.2 equals the logarithmic value of the concentration of the conjugate base ratio over the acid. Now for this next move, to understand this equation, we have to understand a little bit about logarithms. So when we just write the logarithm without the base, we mean then it is the logarithm with the base of 10. So for example, logarithm of x equals, let's say, 5. So what does that mean? It means that logarithm with the base of 10 of x equals 5. That to crack this logarithmic equation, that means that 10 to the power of 5 equals x. Okay? So that would be, let's say, x equals, right. So this is the logarithmic value. So now let's raise this equation out of the logarithm. So that means that 10, so that means that we have the logarithmic value with the base of 10, and that is our x, okay? A conjugate base ratio over the acid. So what that means is that 10 to the power of 0.2 will equal our x. That will be this ratio of the conjugate base over the acid. So to understand this, so we already have the ratio, which is the ratio in the solution ratio of the conjugate base over the acid equals 10 to the power of 0.2. Now this number is about 1.58 or 1.6. Okay? So what will be our final solution here is that our final thing is that the ratio of conjugate base over the acid in the solution approximately equals 1.6. So we have the ratio, but now we actually have to convert the ratio into the concentrations. So what we had mentioned before is that together the base and the acid amount was 0.1 mole. Okay, so if we subtract the concentrations from these values, is that we have the base concentration that will equal about the 1.6 times of the acid concentration. So that is the basic math, is that if the conjugate base ratio over the acid ratio approximately equals 1.6 and the conjugate base concentration equals this times this. The equation initially is that conjugate base plus the acid, that was together the 0.1 mole. So what would be the final result of it? Is that conjugate base equals 1.6 times this acid concentration. So we have 1.6 times acid plus the acid concentration equals 0.1 mole. So that will be that 2.6 HA concentration equals 0.1 mole. And we are calculating the basic math here, that acid equals 0.1 over 2.6 mole, and it's going to be about 0.039 mole. So this is going to be the concentration of the acid, and remember we have 0.1 mole of the complete solution, or we can just multiply it by 1.6, or we can just do the subtraction of 0.1 minus 0.039. Okay, so we have two ways to calculate the conjugate base here. So it is going to be either 1.6 times 0.039, and that will be about 0.061 mole. And it is also like this is gonna be a little bit more, this is gonna be a little bit less, but if you combine them, it is going to be 0.1 mole. So we already have the concentrations of the acid and the conjugate base in the solution. But another information our case gives us is that the reaction generated 10 micromoles of the hydrogen ions protons in 1 milliliter of total solution. So we have to convert these values now in molarity. So first of all, let's convert the values. The neither micromole nor milliliter is our standard value, so we have to convert them into the standard value. For example, the 10 micromole of hydrogen ions, that will be like 10 times 10 to the power of negative 6, and that will be 1 to the power of 1 times 10 to the power of negative 5. That will be moles of hydrogen ions generated in this reaction, during this reaction. As for the 1 milliliter of solution, we have to convert it in the liters, into the liters. So 1 milliliter is going to be 1 times 10 to the power. So now let's calculate the molarity of the hydrogen ions in the solution. Molarity is how many moles of the ion is in solutes is in 1 liter of solution. So moles per liter is molarity. So molarity for the hydrogen ions will equal to 1 to the power of 1 times 10 to the power of negative 5 divided by 1 times 10 to the power per liter, and that is 1 times 10 to the power of negative 2, so 0.01 m, which is molarity of the hydrogen ions generated. Now the next thing is that 1.1 of the hydrogen ions, that will change, that will increase the acid, and that will decrease the conjugate base, because the hydrogen ions that are generated, it will bind the conjugate base and make it into the acid. So hydrogen ions that are generated, it will consume the base and it will generate acid. So we have the original values, okay, of the acid, and new acid will be 0.039 plus 0.01, okay, and the base, conjugate base of mu will be that 0.061 minus 0.01, okay? So again, these are the approximate values, not the absolutely correct, 100% correct values, because remember from there on we have the approximation of the values here. So what will be the final result here is that 0.049, and here we will have 0.051, and if you sum them up again, it will be the summary will be still 0.1. It is very important that it will stay the same molarity, will just change the level of the weak acid and the conjugate base values. So here we already have the new amount or concentration of the acids and the conjugate base in the solution. So our final goal is to calculate what will be the pH with the concentration of this acid and this base. Now that we have the new values of the acid and the conjugate base concentration, we'll go back to the Henderson-Hasselbalch equation one more time and calculate the new pH. So pH, again, Henderson-Hasselbalch equation looks like this: pKa plus logarithm of the conjugate base concentration over the weak acid concentration. So if we put now the values here, is that pH equals 7.2, and it was our pKa plus the logarithmic value of the new conjugate base concentration is 0.051, and that is going to be over 0.049. So now the equation, the actual calculation for this is going to be that pH equals 7.2 plus logarithm. So this value is going to be approximately 1.04. Okay? Now, so same as before, we have here a logarithm with a base of 10. So what that means is that we have to take 10 to the power of something to get, as a result, to get 1.04. So we can do it with the help of the calculators, and the result of it will be 0.018, and it is approximated as 0.02. So pH of the new solution then will be 7.2 plus 0.02, which will result in 7.22 approximately. If you got to this point, thank you for watching. I hope you understand. This was my explanation, and have a nice day.